Today, I supposed to do another few questions from this lesson, and we have another last theory part, that is the de Moivre's theorem. Right. At the moment, almost all finish of the theories in this lesson, except that de Moivre's theorem we finished, and I hope that you are okay with this lesson, so that you have a certain sort of confidence of working out questions. Have you? If not, people, that will be okay once we do another few sums, right? Okay, so anyway, people, soon after finishing this lesson, it's better to do the questions from the very beginning again and again until you're familiar with that. Okay, today, people, I supposed to do the 2020 question, last year paper question. In that paper question, there are 3 parts. Under question number 13, this question came. It's part A is the matrices part. Part B is the complex number part, and part C also in the complex number coming under de Moivre's theorem. De Moivre's theorem, people will discuss that part. We can discuss later. Now, I put that question into the group. I think everybody received that. Then shall we start the question in 2020? See, people, the question is very similar to the past paper sum. This kind of paper question we have done, people. In the class also, we have done this kind of question. This is very similar to a past paper question. So that is why I'm always telling you to do the past paper sums before going to the examination. So then when you go to the question part B, people, have you got this question? Did you have the question at the moment? Yeah, I think so, right? Wait for a while. Right, people, now the question says something like this. 2020 question. Given that let Z, W elements in set of complex numbers. This notation. Show that mod Z squared is equal to Z bar. Right? And given and applying it to Z minus W. Show that this answer. Z minus W mod perfect squared is equal to mod Z squared minus 2 times real part of Z W bar plus mod W square this way. Right. People, last week, the Sunday group recording, I put to the group. Did you get that note? Completely a separate part I finished there. Did you all get these notes last Sunday? Group recording I put to your group 2 and the proper online group 2. Yeah. Everybody must complete the notes, people. I did this one, otherwise that part today we have to do. So wasting time. So therefore, please, those who are not, those who didn't get this yet, people take that one and complete the notes, right? That's another separate part. Okay. During 3 hours, I completed last week there. Okay. Yeah. Okay. Now, before deleting the recording, some recordings people deleted. Right, here and there randomly. Now my cloud space is full now. Now always I am getting what messages asking to purchase for new storage, but it is not possible to pay more money. No money. We don't have money now. So therefore, as soon as possible, get the recording and cover up with. We can't say which recording will delete next. Randomly here and there recording delete. Okay, this is done by the Zoom, not by us. Right, so therefore, better thing is, soon after getting you the link, go through that can as soon as possible cover up the notes, right? And now we are here. Next thing is this. This one you can prove. Show that this no mod z squared is z bar. So now we can take for z this x plus iy. Then you can very clearly understand. Then you can write z bar going to be x minus iy. And now also people mod z squared. You know, real part perfect square plus engine part perfect square is the mod z squared. Okay, right. Now people to prove this one, what I do is this. I take z bar, this we have done, but I am going to do this one to give you the idea about getting marks, right? Z bar people, x plus iy, x minus iy. So then when I multiply this, we get a plus b into a minus b means x a minus a squared minus b squared. B squared is this, right? I squared is minus 1 and plus 1 we get like this. And this is nothing but people mod z squared. So then this gives us mod z squared is equal to z bar. Okay, right here people write in this way, 5 marks given, and for the final answer 5 marks given. 10 marks coming for this, right? Okay, the next part is applying it to z minus w, right? People now here when we consider a complex sum z, when the complex sum z is multiplied by its conjugate, what you get is it is given the perfect square of the modulus of this z, mod z perfect square. Okay, that's what we get. So therefore, in order to get modulus perfect square of the modulus of a complex number, what we need to do is people, the complex number should be multiplied by its conjugate. Then that product will give the perfect square of the modulus of that complex number. Okay, right. So then here, next one is we are asked to find this here. Z minus w, Z is a complex number, W also a complex number. Then Z minus W, that difference is a complex number. Its modulus perfect square only asking. So therefore, anyhow, this Z minus W is a complex number. For this Z minus W, we can give one answer like this Z1, right, of the form x plus iy for this difference, because we know difference of two complex numbers is another complex number we have proved. Now its modulus perfect square only people we need. Okay. Then here, if we need to get the perfect square of the modulus of a complex number, this suggested multiply that complex number z by its conjugate. So then using that, we can now find that answer, right? What z minus w modulus perfect square, then you can write people, write this z minus w, z minus w modulus perfect square is equal to z minus w times people its conjugate, this way, right? But you know, this way, conjugate of a difference, we can write, apply this conjugate for this z and this w. Okay, that we learned under theories here. This one we proved, no? Okay, this one we proved. Now I can put this conjugate for this z as well as this w like this. Now this and this you can multiply z bar, this and this you can multiply z w bar, and here minus w z bar minus minus plus w bar. Like this you can write. Okay. Z bar mean people mod z square. Here you can take minus sign out. Then we get within bracket like this. W bar means people perfect square of the mod w. So here we have z minus w mod perfect square like this. Okay. Now asking this way, right? People now here this z and this z both are the same, right? Right. Now I'm going to take this one. R here we are given z w bar, right? Just think like this. Lit, right? The steps I am going to write next, not mentioned in the marking scheme, but I am going to write that steps also for easy understanding, right? Even I am going to write that Z1 complex number as this is the W bar. This way I am going to write. Then if I take people, the conjugate of this Z1, that is nothing but conjugate on the right hand side, no, this. Then this conjugate we can apply on this Z as well as this W bar. This is nothing but Z bar, W bar is W. Then you can very clearly understand, if you take this as your Z1 complex number, Z1 bar going to be WZ bar. WZ bar. This is Z1 bar. Right, people? Then here we have what? Complex number plus its conjugate. Complex number plus its conjugate. People, sum of the complex number and its conjugate, you know what, people? 2 times real part of Z. Right? That means, for example, see people here, the very simple theories applying everywhere. So those theories we should be able to get at once, right? For now, example, if I take Z dash x plus iy, Z bar going to be x minus iy. Okay. And once you add them up, you can very clearly understand these two will cancel off 2x. What is this x? Real part of Z. Therefore, this is nothing but this Z plus Z bar. Okay. Now here also we have here Z1 plus Z1 bar. Then for this sum I can write a real part of Z1, right? Real part of Z1, right? Real part of Z1. Now this one people directly you can use without proof, right? Even at the marking that has been used directly. Right, so then I can write people this Z minus W mod perfect square is equal to this one. And minus this is now 2 times real part of Z1. Now, Z1 is people this, no? ZW bar. Plus this mod W perfect square. This is how we take that answer. Okay, first answer coming. People, can you remember a similar question we did? Last year also the same series of questions I did in the tutorial. The last tutorial only people still are having, right? The same tutorial. I didn't change that tutorial because some important questions are available in that. See here, when you go through your tutorial, can't you find a question subject this method you simplified and got the answer available? Okay, yeah. Now other thing is people write this expression, similar expression for 1 minus Z W bar modulus perfect square, right? Then think it like this. First is 1 minus Z W bar modulus perfect square. They are asking people write a similar expression. Write a similar expression mean no need to show the steps in getting that answer. No need to write the steps. Right. How to write people? You match like this way. This Z I take as 1 because this Z is a complex number. No? 1 also a complex number. We said real number is a complex number. Right. And this as this W, I take this whole thing Z W bar. Okay. Then we can match it like this. As in this simplified expression, we take that Z as 1 here. So dash 1. This Z I take as this one, and that W I take people here is a W bar. Then what I do is in the expression, this right hand side expression, every Z I put people that one, and the rest W bar I can take no by that. Then I write like this. This way I can write Z is now 1, its modulus perfect square minus 2 times real part. This Z this one. W bar. What is W? Z W bar. Then Z W bar whole thing conjugate. Right now? And mod W square. W is this. Z W bar mod perfect square. That way now you can write. Just to match the result this with the one we need. Mod 1 square is equal to 1. This is 1. When I multiply this and this, when you multiply something by 1, it won't change, you know. Then you can put here. Because now here, when I take this bar to this Z, this will be Z bar. To this W bar, what do you get? W bar bar. It is W. Then this 1 minus 2 times real part of what? Z bar W. And here, people, you can, if necessary, write this modulus perfect square. No, you know that we have learned Z1, Z2. Write that here. Z1, Z2 mod. People, we have written how? Mod Z1 into mod Z2. No. Then if we have square here, the same thing we can apply. So then I can write here this one how, people? Mod Z perfect square mod W bar perfect square. That way you can write. Okay, right. People, this is what we get there. This is the one we get. Right. Now, though we put this conjugate for this Z and this W bar separately and to get this one, people see here, when I consider the complex number Z, x plus iy, its real part is what? Real part is x. I'm going to consider its conjugate, x Z bar, x minus iy. What is its real part? Also x. The right hand sides are equal. Then this implies us what, people? Real part of Z is equal to real part of Z bar. What is meant by that, people? When we consider the complex number and its conjugate, the real parts being equal. Then people here just thinking, right? Here, real part, this 1 and this when you multiply people, we get, I'm going to write it again, 1 into this mean people, the same thing, this is coming. Right, I am going to write it as before like this, Z W bar, right? And whole thing when you get no, the same thing I wrote here. Okay, now according to this, real part of Z and real part of its conjugate. Okay, conjugate complex number real part and complex number real part, both are equal. Then people, since here also we have real part of Z W bar conjugate. You know Z and W bar when you multiply, you get a single complex number. Why? You know product of any two complex number is another complex number. Then really this one I can consider as Z1. What? Z1 is this Z W bar. Okay. Now what real number we need? Z1 conjugate. Its real number, its real part only we need. Its real part only we need. But we now here real part of Z and real part of Z bar being equal. So therefore, people, we need the real part of conjugate of this, real part of conjugate of this complex number. But that real part is equal to real part of Z W bar. Then I can write here without this conjugate, I can again write this is equal to real part of Z W bar. Okay, that thing you have to get to your mind. Okay, so then I can write. These are very simple things, right? Okay, now you can write this one. Since real part of Z W bar conjugate is equal to real part of Z W bar. I can write for the place of this again, real part of Z W bar. 1 minus Z W bar modulus of x square is equal to 1 minus 2 times real part of Z W bar this. And people, omega bar modulus. You know, modulus of Z and modulus of conjugate of Z be equal. Then here omega bar modulus perfect squared I can write as omega modulus perfect squared. This way we can write that. This way we can write that. So then here the things you should know, people. Here is real part of conjugate and complex number. Real part of Z and real part of Z bar being equal. That idea we use. And modulus of conjugate and modulus of the complex number also be equal. That we use there. Right? They are very simple things, people. When you work out questions, automatically these ideas you get. At that moment, you should be able to insert this at the relevant places. Other than that, people, this question is really nothing. Okay. Right. Now, what is asking next? Okay, now here the mark distribution when I give you. For the first part, people prove in this 5, 5, 5, 15 marks coming. For this one, 5 marks given. And apply this conjugate on this and this, we another 5 marks. And finally, given people for the last answer, another 5 marks given. For the last answer, 5 marks given this. Right. And people, this one given only 5 marks. Huh? Given only 5 marks. Right. Now, what is next? Next part asking this. And show that this answer. Show that this answer. Right. Then what we do is this, people. I am going to take this answer as number 1. This answer as number 2. Now take 1 minus 2. Now take 1 minus 2. First take 1 minus 2, people. I take 1 minus 2. Take this 1 minus 2. Right. When you take 1 minus 2 to left hand side, what do you get is Z minus W mod of x squared minus modulus 1 minus W bar of x squared. Then, what do you get here? This minus 2 here is a W bar. Minus 2 here is a W bar. That 2 we can cancel out. Right. Then here we get mod z squared of x squared plus here this minus this, then this no, right. That middle term will cancel out. Okay, so then now we get 1 here plus mod z squared mod W squared. Right now, last answer asking people, I remove the bracket here and here I take minus sign out. Once I take minus sign out, the bracket we get here now plus 1 here minus mod z squared. And people here, this one and this one, when I consider, I can take their mod W of x squared out as common factor. This is now 1 minus this one mod z squared. Then this one again common, take it out, minus, what is the answer asking? Right now, 1 minus mod z of x squared, right? When I take this with minus sign out, this is now 1. You know what W of x squared is. We get this answer. This is the correct answer. Right? Right. Okay. Right. What's the last part? Deduce that if mod W equals 1, if mod W equals 1, what happens, people? This is 1. 1 squared is 1. Then this bracket will be 0. If this is 0, this product will be 0. The right hand side becomes 0. Okay. Then this gives us people this z minus w mod perfect square minus 1 minus z w bar mod perfect square will be equal to 0. Take this right hand side, right? Right, and people here we get mod w equal to 1 and another one given is it not equal to w? Is it not equal to w? Yeah. Then I can take the positive square root on both sides. But the reason, people, mod is always positive value. Modulus means positive value. Then we take the positive square root. Then this is equal to this. Right. Now I divide both sides by people. I divide both sides by the right hand side. Divided by this 1 minus z w bar. What do you get there? Z minus w mod divided by 1 minus z w bar mod is equal to 1. People, how do we know that this is a value? No? This is a real number really. Why? Modulus of a complex number is a real number, positive real number. Or 0. Modulus can be 0. No? People, how do you know that this is not 0? Because if this is 0, a real number divided by 0 is people undefined, infinity, undefined. This is not 0. The reason is this. We know we are given that z complex number not equal to w. Then I am going to multiply both sides by people w bar. I multiply both sides by w bar. When I multiply both sides by w by bars, still this inequality sign will be there. W bar. Then we get, what is w bar? Mod w perfect square. Is that w bar not equal to mod w perfect square is 1. Clear no? Is that w bar not equal to 1? These two are not equal. Then the difference will be equal to 0. For that, to give this idea only, people, to emphasize that only, is that not equal to w given. Right? Is that not equal to w? Then I multiply both sides by w bar. Then we get like this. This is mod w perfect square. It's 1. Is that w bar not equal to 1? Right? Okay, now we came up to this. But even we know another one like this. We have proved this one also. Z1 divided by Z2 modulus is equal to Z1 modulus divided by Z2 modulus. This we have proved. Then this right hand side only, people, here we have complex number modulus divided by another complex number modulus. Okay. So therefore, this moduli at the numerator and denominator we can apply separately. So then we can write this how z minus w divided by 1 minus z w bar equals 1. This is how we take that answer. Right? People, it's next part, the De Moivre's theorem part we'll discuss later after studying that. Now the marks given, people, like this. Yeah, taken here. Yeah, people showing up to here, taking 1 minus 2 for the step this 5 marks given, simplification 5 marks, and final answer 5 marks, right? For this one 5 marks, this one 5 marks, and this one 5 marks. 30 marks given for that. And yeah, for the step this 5 marks given, right? And For the final answer, another 5 marks given this. Right. So that's how we get the marks. Is the 20 question? See, it's a very easy question, and the De Moivre's theorem part also very easy part, right? When we discuss that question, you will find the overall question paper complex number question is a very easy question, but you can very clearly understand the theories you have to remember. Otherwise, people you can't approach the answer because answer is there, but you don't know in that the answer contains because of you don't have a good memory regarding the theory. So therefore, those theories people again and again get take to a short note and don't go to by heart. Only thing is do the same questions again and again. Once you are working out a question, if you can remind these theories, that is the important thing. Just by hearting them without any reason, people, no use. At the moment you need to get use of that, people, you have to do the questions, and while you are doing question, you should remind them. Then only at any question when you work out, people, that idea fall into your mind. Okay, right. So now, next question I am going to discuss is, people, 2017 question. That was a very easy question, right? That was a very easy question. That question also I put today to the group, right? And take that question 2017. Take 2017 question, people. That's also available in the group, right? Read that 17 question. Sketch in an Argon diagram the locus C of the points representing complex numbers Z satisfying mod Z equals 1. Mod Z equals 1. Mod Z equals 1. Asking to sketch the curve, the locus C of the points. People, what is that? This Z mod Z equals 1. I can write Z minus 0 mod equals 1. What is this really? This is a circle with center at the origin and radius 1 on the Argon plane. No, right. This way. This one is the C. Now is this. Okay, next one given, people, is a knot. It's a knot given in the polar form A times cos theta plus I sin theta. Right. And there we are given A positive and this theta between 90 and 0. This way we are given that. What is asking there? Asking this, people. Find the modules in terms of A and the principal argument in terms of theta of each of the complex numbers 1 upon Z naught and Z naught square. 1 upon Z naught and Z naught square. 1 upon z naught mean people 1 over z naught is this no a cos theta plus I sin theta. Then we'll multiply 1 upon a I keep like this cos theta plus I sin theta. By its conjugate, we multiply both numerator and denominator. Right. Then this is cos theta minus I sin theta divided by cos theta plus I sin theta times cos theta minus I sin theta. Right? Then here we have a plus b into a minus b form. That is a squared minus b squared. That means square of this minus square of this. Then here we get I squared is minus 1. That minus and this minus make plus. Then here we get cos squared theta plus sin squared theta. Okay. 1 upon a cos theta minus I sin theta, right? Divided by cos square theta plus sin square theta to the denominator. This is really 1. Okay. Then we can write 1 upon z naught like this. 1 upon a cos theta is minus I sin theta, people. I can write plus I minus sin theta like this. People always remember whenever we keep a complex number in polar form, we should have the form this r, a positive value, and cos theta plus I sin theta. The same angle this should be having here, people. And between these two terms, we should have plus sign like this. And this figure should be positive. Right? Whenever you represent a complex number in polar form, these things should be very important. This figure should always be positive value. This angle and this angle should be equal, and in between these two terms, plus sign should be available. Then this is of course in that form, but here we have minus sign. Then what I do is this, people. This minus sign we bring inside this. Okay, because we know sine minus theta is equal to minus sine theta. The minus sign with the angle we can take out. Similarly, when the minus sign is before sine ratio, that can be put in the angle. Right? So therefore, I can write it like this. 1 upon a. I will keep for a while as this same. This one I can write I sine minus theta like this. Huh? But people, you know, cos minus theta. Cos minus theta is cos theta. Okay. Then this cos theta I can write as cos minus theta. Because this one changed. Because cos minus theta is cos theta, you know. Then, as I told you, this all requirements available here. This is positive because a is positive given. The same angle we have here between these two terms, we have plus sign. Now only 1 upon z naught complex number we have really represented by the polar form. So therefore, now we can decide. You can determine this figure only the modulus of the left hand side. This angle only the argument. So now you can decide, determine the argument. What is the argument? What is the modulus? Therefore, 1 upon z naught modulus is equal to people 1 upon a. And what is the argument? Argument of 1 upon z naught is this minus theta. This is minus theta. Correct, no? Right. Okay. Like that, take Z0 square. We need to take suddenly Z0 square. Multiply Z0 by Z0. Okay. And I'm going to take now Z0 square, right? Z0 square mean A cos theta plus I sin theta perfect square, right? Right, perfect square. Right. So then we get Z0 square is equal to square is A square. Now square of this. What is that? Cos square theta plus 2 times I sin theta cos theta plus what people? I squared sin square theta. I squared sin square theta, right? I squared sin square theta this way. Right now, here I squared is minus 1 minus sin square theta, here cos square theta. Then here we have A squared. This is cos square theta minus sin square theta, right? Okay. And here I times 2 sin theta cos theta is sin 2 theta, no? Sin 2 theta. And people, you know, this cos square theta minus sin square theta also what? That is cos 2 theta, no? That is cos 2 theta. Right. So then we get Z0 square is A square. This is now cos 2 theta plus I sin 2 theta. Okay. Then here this is a positive value. This angle and this angle the same. Between these two terms, we have plus sign. So therefore, the Z0 squared complex number now we have really represented by the polar form. So then you can now write Z0 squared modulus going to be this A squared, no? In argument of Z0 squared going to be this 2 theta. Right? That 2 we found now. Right. So we got that. Right. Even now, give another one. What's that? Let P, Q, R, and S be the points in the above argon diagram representing the complex numbers. Is it not? Yeah, we'll see. The point P gives the complex number. Is it not? Point P gives the complex number. Is it not? And the point Q gives represents the complex number 1 upon Z naught. And point R gives the complex number Z naught plus 1 upon Z naught. And point S gives the complex number Z naught square. Right? Yeah. People, let's see what is this Z naught plus 1 upon Z naught complex number. That also we should find here. This I think you can understand correctly. Right. So now Z naught plus 1 upon Z naught. Z naught plus 1 upon Z naught is equal to Z naught means A times cos theta plus I sin theta. Right. We'll find that later, people. Much easier to discuss that part later. Right. Now, show that when the point P lies on the C above, C means this circle, people. Its center is and origin and radius is 1. If P lies, when the point P lies, P gives a complex number. Is it no? Is it no? So that this P here representing the complex number, is it not? Then people, if P lies on this C, the distance from origin to this Z0 complex number is this radius, no? The distance from origin to the complex number only we define as people modulus of the complex number. But the modulus of the complex number Z0 is A. Then you can write when P lies on C. Z naught mod should be equal to 1 because radius of the circle is 1. But Z naught modulus means this figure A. Therefore, A equals 1. A equals 1. Right? Secondly, people asking to prove what? The points Q and S. Q and S. Q is 1 upon Z naught. 1 upon Z naught, argument is minus theta. Somewhere here. Right? 1 upon Z naught. This 1 upon Z naught is represented by the point Q. This is Q. We have to prove Q and S also lie on C. Correct? No. 1 upon Z naught modulus. People we found earlier as 1 upon E. Since what is A, people? 1. We proved here. Since A is 1, we can write 1 upon Z naught mod should be equal to 1 upon 1. 1 upon Z naught mod is equal to 1. The modulus of this complex number 1 upon Z naught is 1. That means the distance from this origin to this point Q should be 1. Therefore, Q should be on the circle because circle has radius 1. Therefore, Q lies on C. Right. Next one, people ask you to show S. Z naught squared. Z naught squared, the argument is 2 theta. I take somewhere here is point is gives us Z naught squared. Z naught squared modulus. We can write Z naught, right? Square modulus, no? We found A squared. There I have written down that as Z naught modulus perfect square. This is equal to Z naught squared modulus, right? Okay. So this is people A squared, but A is 1 square. This is 1, right? Then Z naught square modulus 1 means the distance to this S from the origin should be 1. That means S also on the circle C. Therefore, S lies on C. Right. Next one. Next one, people asking like this. The point R lies on the real axis between 0 and 2. R represents this complex number. And then we'll find Z0 plus 1 upon Z0. Z0 plus 1 upon Z0. Z0 A cos theta plus I sin theta. People, Z0, 1 upon Z0. We found 1 upon Z0 as 1 upon A cos minus theta plus I sin minus theta. We obtain this answer, no? We obtain this answer. No? But since A equals 1, we found, no? A equals 1. Now I can write substitute for A 1 here and here. Then see what you get. Z0 plus 1 upon Z0. If we get A cos theta, that means 1 cos theta plus I sin theta. The 1 upon 1 is 1 cos minus theta plus I sin minus theta. I sin minus theta. Right? Because this minus sign of this theta, you can take before. And you can write that as minus I sin theta. Right? This is now minus I sin theta. This plus I sin theta and minus I sin theta you can cancel now. Cos minus theta we can write as cos theta. Then cos theta plus cos theta is 2 cos theta. You see we did. Right? Now let us ask you next. Point R. That means R represents this complex number Z0 plus 1 upon Z0. R lies on the real axis between 0 and 2. Real axis. Even you can very clearly understand this cos theta is a real number. Multiply that by 2, 2 cos theta is a real number. So therefore Z0 plus 1 upon Z0 is a real number. Right? You can write 2 cos theta is purely real. Right? So therefore Z0 plus 1 upon Z0 is purely real. Understand? Okay. But this complex number is represented by the point R. Therefore, point R should be on the real axis. Now, furthermore, we are asked to show that point R lies between 0 and 2 on the real axis. That can easily be proved like this. You know, people, theta. We are given theta less than theta less than pi by 2, greater than 0. Given that theta less than pi by 2, greater than 0. In this inequality, we take cos. Once we take cos here, what do you get? Cos 0, cos theta, cos pi by 2 like this. Then once you take cos in this inequality, people, the inequality gets opposite this way. Cos 0 is 1. Here cos theta, cos 90 is 0. Okay. Now this inequality I multiply by plus 2. Whenever we multiply an inequality by plus value, the directions won't change. If I can write it like this. Two greater than 2 cos theta greater than 0. But this 2 cos theta is nothing but people Z0 plus 1 upon Z0. This gives us 2 greater than Z0 plus 1 upon Z0. Then you can very clearly understand this 2 cos theta is purely real, we said. Therefore, this Z0 plus 1 upon Z0 is purely real. Therefore, the point that represents this complex number should be on the real axis. Since its size is greater than 0 and less than 2, that point R should lie between 0 and 2 on the positive real axis. Understand? Therefore, we can write, therefore, point R should lie on the real axis between 0 and 2. 0 and 2. Correct, no? That's how we take that answer. Right. We will now take 2019 question. 2019. That's also another good question. 2019. Take 2019 question. Who did this 2019 question as homework? Yes. Right. Now, there you are given, people. Z1, Z1, Z2, right? Z1, Z2 are complex numbers, right? Show that. First one is real part of Z. Real part of Z less than or equal to mod Z, right? Mod Z. Okay, no, that we have already done, right? People, I said you that in any question, most of the time, the parts we proved so far, 1 or 2, or sometimes more than that, may be available. So therefore, all the proofs I did in the lesson, you have to practice again and again, people, right? Yeah, if you don't do this question, people, then no point of learning that matrices part. The matrices is the first part of this question. So matrix is also very easy one. No? It's also very easy one. So therefore, practice this. Right. This one, okay, we did. Well, second part, also we have done. Z1 divided by Z2 modulus. Ask him to prove Z1 mod divided by Z2 mod. This also, people, we did in theories. We did in theories. Therefore, I skipped them, right? Ask him to reduce this, right? Real part of Z1 divided by Z1 plus Z2, right? Less than or equal to mod Z1 divided by mod Z1 plus Z2. Subject to a condition. What is the condition, people? For Z1 plus Z2 complex number not equal to 0. Right, people, the reason is, if this Z1 plus Z2 equals 0, then here, this within bracket, we have a complex number. No? Then Z1 is a complex number. Z1 plus Z2 is a complex number. Division of two complex number we have here. Division of two complex number is another complex number. But if Z1 plus Z2 equals 0, this denominator 0, then this within bracket, the complex number becomes infinity. Infinity is undefined one. No meaning. To avoid that meaningless complex number coming to this within bracket part only, people, this is given Z1 plus Z2 not equal to 0. Right? Now, how to prove this? People, you can very clearly understand this way. We can write, let Z dash Z1 divided by Z1 plus Z2. Right? Z1 plus Z2 is a complex number because we have proved sum of two complex numbers is complex number. Then denominator is a complex number. Division of two complex number, we have proved people that also another complex number. So therefore, this Z1 divided by Z1 plus Z2 whole thing finally a complex number. That complex number only people I took as Z dash. But now we have proved here like this. And then using this, therefore, real part of Z dash should be less than or equal to mod Z dash by applying this result. Because we proved this result. That one we apply for this complex number Z dash. So then Z dash is this. Real part of Z1 divided by Z1 plus Z2. Less than or equal to modulus of Z dash here. This way. Now people, for this, okay, I can apply this result here. Division of two complex numbers, modulus, is equal to, right, modulus of their division. Sorry, the division here we have first taken modulus, division of the modular values of the complex numbers. That means people, Z1 divided by Z2 modulus, this modulus we can apply for the numerator and denominator like this. Then once we apply that one, we are here people, this one I can write mod Z1 divided by mod Z1 plus Z2. This way I can write. Correct, no? And this is true for, right, Z1 plus Z2 not equal to 0. Right. Now people, next one asking, verify that verify that real part of Z1 divided by Z1 plus Z2 plus real part of Z2 divided by Z1 plus Z2 equals 1. How take that? If we want to get this answer, we can very clearly see this result. This you know already. Right? If I consider a complex of Z1 as x1 plus iy1 and another complex number Z2 as x2 plus iy2. iy2. This x1, x2, y1, y2 are real numbers. You can very clearly understand real part of Z1. What is that? x1. Real part of Z2. What is that? x2. That's well obvious. Okay. You have to write down this as a note, people. Huh? These are very important things. Now I am going to add Z1 plus Z2. here, x1 plus x2 plus, take this I out, y1 plus y2. Okay. Then I am going to write the real part of this z1 plus z2. It is this. What is it? x1, real part of z1. x2, real part of z2. And this is real part of z1 plus z2. See here, this relation is very important to get the next answer. What is the result? There are two complex numbers, right? Z1 and Z2. The real parts of them we add. There are two complex numbers, Z1 and Z2. We separately find real part of Z1 and real part of Z2. And we add them up. That sum is equal to, by finding sum of Z1 and Z2, and of the resulting complex number, we take real part. To that, this sum equals. Now, once you go to that part, people, what is the next part? What is given? You can write on this as a note. What is next thing given? Next thing given is this. Real part Z1 divided by Z1 plus Z2 plus real part Z2 divided by Z1 plus Z2. People asking this to show this is equal to 1. People, what is this? Z1 divided by Z1 plus Z2. A single complex number. Its real part. This one, another single complex number. Its real part. Then here what do you have? Sum of the real parts of two complex numbers. That means like this. Sum of the real parts of two complex numbers. This says it is equal to this. First add in the complex number and find in real part of that. So therefore I can write this one as how? This is equal to people real part of what? This complex number and this complex number. Z1 divided by Z1 plus Z2 plus Z2 divided by Z1 plus Z2. Then you can see, take in common denominator, right? Once I simplify this, what do you get? Z1 plus Z2 divided by Z1 plus Z2. Cancellation, these people, we get real part of complex number 1. This is a complex number, people, 1. This one complex number, if I write, people, it is 1 plus 0i. This is the complex number Z now. There we have. What is the real part of that? 1. Yeah. This one we can write as 1, no? 1 plus 0i. Because we got only 1. I write that as 1. Real part of this one I am going to write as 1 plus 0i. Complex number is 1 plus 0i. What is the real part? Real part is 1, people. Right? Real part is 1. So what is asking? Asking to show real part of this plus real part of this. Right? It is therefore 1. Real part of this plus real part of this is equal to real part of the complex number 1. Real part of the complex number 1. Real part of this complex number. Real part of this complex number is really this one, people. This one. This is a complex number. Its real part. What? 1. This one. Therefore, this one is equal to 1. Then you can write real part of Z1 divided by Z1 plus Z2 plus real part of Z2 divided by Z1 plus Z2 equals 1. That we got. Well, this is also true for this Z1 plus Z2 not equal to 0. Why? If this Z1 plus Z2 equal to 0, people, this is 0, this is infinity, infinity has no meaning. Then this statement has no meaning if this Z1 plus Z2 equals 0. Right. Now what is next? Now ask and prove this, say people. Show that Z1 plus Z2 mod less than or equal to mod Z1 plus mod Z2. That we have proved, but using this result now we have to prove this. Right. To get the last answer, I can use the result this. We proved, people, at the very beginning of this question, real part of Z1 divided by Z1 plus Z2 less than or equal to mod Z1 divided by mod Z1 plus Z2. We proved this, no? We proved this. We proved this. Take this as 1, proved. Right. And similarly, we can write, people, similarly we can write real part of, put in here for this Z1, I write Z2. Z2 divided by Z1 plus Z2. This one, the same way I can write, people, here, mod Z2 divided by mod Z1 plus Z2. Number 2. Okay. Now we add this 1 and 2. Two inequalities we can add, no? Left hand sides together, separately the right hand side together. Then what do you get? Real part of Z1 divided by Z1 plus Z2 plus real part of Z2 divided by Z1 plus Z2 less than or equal to, people, this mod Z1 divided by this mod Z2 divided by this here. But short while ago, people, we proved this as 1. A moment ago, we proved this is 1. This sum is 1. Then I can put 1 here. And then this gives us what, people? This gives us 1 less than or equal to mod Z1 divided by mod Z1 plus Z2 plus mod Z2 divided by this. Right. Now I can multiply this by mod Z1 plus mod Z2. So this is mod Z1 plus mod Z2. Mod Z1 plus Z2. Mod Z1 plus Z2 less than or equal to mod Z1 plus mod Z2. Because this inequality we proved in 2 ways, geometrically and algebraically. But the same thing now we have obtained. But people, this is also true because up to this answer, we have used this relation. No? Can you remember this relation we proved? This is true for Z1 plus Z2 not equal 0. No? This is true. We proved that. When we were proving this, people, we mentioned at the side after proving that this is true for Z1 plus Z2 not equal 0. The same thing here and here we have used. So therefore, by using them, the result we obtained is also true for Z1 plus Z2 not equal 0. Okay, then we have mentioned that. Why? This answer we obtained based on this and this. But these two are true subject to Z1 plus Z2 not equal 0. Using that too, if we derive something, people, the final answer also true subject to this condition. That is why I wrote this. But in the question asking, not only for this Z1 plus Z2 not equal 0. Question asking people for any Z1 and Z2. For any Z1 and Z2, this is true. That's what we have to prove. Whichever this Z1 and Z2, sometimes that Z1 plus Z2 sum can be 0, even though this should be true. But we have proved this is true for Z1 plus Z2 not equal 0. But we need to prove for any Z1 and Z2, this result become true. People, this result become true subject to this case. So therefore, this result is true. Z1 here taking this Z2 to the right hand side minus Z2. When this Z1 is not equal to minus Z2, then Z1 plus Z2 not equal to 0. For that case only, this is true according to our proof so far we obtained. But people, this is not the one asking in the question. Question asking for any Z1, Z2 in complex numbers. This is true. Even this case also, this should be true. Then another one case we have to prove to complete the proof in the question asking. Right? People, what if this Z1 and Z2 equal to 0? Then after this, people, we can write when Z1 plus Z2 equal to 0, Z1 plus Z2 is a complex number. It is now 0. Complex number 0 means, people, its modulus also 0. Then Z1 plus Z2 modulus equals 0. When the modulus of Z1 plus Z2 is 0, people see whether this is true. This is 0. This can be 0 or positive value. This can be modulus of people. Modulus of a complex number is always a positive value or 0. This is now 0. This can be 0 or positive. This can be 0 or positive. If both are 0, 0 plus 0 is 0. 0 equals 0, left and right become equal. Otherwise, the right hand side greater than the left hand side. Therefore, this relation is true for Z1 plus Z2 mod equals 0 2. This one. Therefore, we can say what? 0 less than or equal to mod Z1 plus mod Z2. True. When Z1 plus Z2 equal to 0 case also, this becomes true. Then people, this is true for any two complex numbers Z1 and Z2. Right? Then write down that. Therefore, hence, mod Z1 plus Z2 less than or equal to mod Z1 plus mod Z1 become true for any Z1 comma Z2 in set of complex numbers. This is how we prove that part. People, it's part C also by De Morgan's law. Sorry, De Moor's law. De Morgan's is coming in probability. De Morgan's. De Moor was coming in this complex number, right? By De Moor's theorem, we can prove that. I'll come to that after doing this De Moor's theorem next day, right? People, the next question is the question in 2018 paper. Take your question in 2018, right? 2018 people. Right. Take 2018. Take this. Right. You are given let z x plus iy, where x, y both are real numbers, right? X plus iy, x, y both are real numbers, right? Define the modulus mod z, then the conjugate z bar of z that you know, and asking to prove z bar mod z squared, z plus z bar 2 times real part of z, and z minus z bar 2 times I imaginary of z. That also, people, the whole thing we have proved under theories. So no point of doing them again and again, right? That's why I asked you to people, do this all proof I did. Okay, do this all proof we did in the class. They are very important, people, right? Yeah. Now that proving part you can very easily manage. So therefore, I'm not going to do that again. No point of wasting time, right? Now, given this way, a complex number W given as complex number W given as 1 plus z divided by 1 minus z. Z not equal to 1. Complex number W given as 1 plus z divided by 1 minus z. Here given z not equal to 1, you know the reason. If z equals 1, this is 0. Something divided by 0 is undefined. Yeah, z not equal to 1. Show that a real part of W is this. And the imaginary part of W is this. Yeah. And then we'll write like this. This W is a complex number. You know why is it called as complex number? The right hand side, this numerator, here sum of two complex numbers, no? Sum of two complex numbers is a complex number. Denominator, difference of two complex number, also complex number. Division of two complex numbers is another complex number. That is why we say this W is a complex number. Now what I do is, people, this numerator and denominator, we multiply by the conjugate of this denominator. Remember, whenever we are given this way a fraction as our complex number, if we work out anything regarding that, we have to convert that to a complex number of the type, the usual type is what people, x plus iy. Then what is the usual way to convert that? Multiplying both the numerator and denominator by the conjugate of the denominator. That is the main tool we use. And then what we do is we multiply people this numerator and denominator both by the conjugate of the denominator this way. Right. Now I can apply this conjugate on this one and this z both. Here also the same way. One conjugate minus z conjugate. Right. Here, the denominator we can write. One minus z is a complex number. It is multiplied by its conjugate. A complex number is multiplied by its conjugate. You know, people, what is the result? Mod z squared coming. Mod z squared coming. So therefore, this is 1 minus z modulus perfect square. This is what we get. Now this numerator, 1 bar. 1 bar is 1, people. 1 bar means conjugate of the complex number 1. It is the same, no? We learned this before this. So then I can write W is equal to 1 plus Z, 1 bar is 1 minus Z bar. This is 1 minus Z mod perfect square. Now we multiply by 1 this and Z this. 1 minus Z bar, Z minus Z bar. Right. Right. Now I can take this Z bar with this 1. Z bar mean people mod Z squared. And here, this Z minus Z bar. I can divide that to separate like this. By 1 minus Z mod perfect squared. People, but we have proved in the same question under theory, Z bar is equal to what? 2 times I imaginary part of Z. 2 times I imaginary part of Z. So then I can write for this Z bar 2I imaginary part of Z, right? 1 minus mod Z perfect squared divided by 1 minus Z mod perfect squared, right? I can write for this one 2 times I imaginary part of Z divided by 1 minus Z mod perfect squared. This way I can write it. Right? Now I can write, people, one minus mod z perfect squared 1 minus this I can write this I before like this. I times 2 times IMZ divided by this. Right now. You can very clearly understand, people, this part is really X. This part is really Y. Here we have X plus IY form as this W. You can very clearly understand this value is a real number, positive or negative, real number. That I took as X. Why? Mod Z means a real number, no? Right? And here also, people, IM is imaginary part of Z. Of any complex number, both the real part and imaginary part are real numbers. So therefore, this is a real number. IM is a real number. Multiplying that by 2, this is a real number. Dividing that by this is a real number. This fraction is real number. Then y is that, y is a real number, right? X, y both are real numbers. Then what is the real part of this W? Should be this. Imaginary part of W should be this. Understand? Right? Therefore, the answer you can write. Real part of W is equal to 1 minus mod Z square divided by 1 minus Z mod perfect square. Imaginary part of W is that 2 IMZ one minus Z mod perfect square. We get. Okay? Yeah. That we got that. Right. What's next? Show further that if Z equals cos alpha plus I sin alpha, Z cos alpha plus I sin alpha. People, here, if I write this one this way, no objection by you. Cos alpha plus I sin alpha, here we have, I write 1 before this. This is the people value, the mod value of this Z. This implies mod Z is 1. Why? People, we said this is the polar form of Z, no? Then before the bracket, what do we have? It is the modulus of that left-hand side complex number. Mod Z is 1. Right. Now what is asking there? Alpha here between 0 and 2 pi, then omega is I cot alpha by 2. Okay. Right. Now, people, you can very clearly understand. Then this real part of W, not omega, W there, omega or W, whatever. Right here, 1 minus mod Z perfect square divided by 1 minus Z mod perfect square. People, this mod Z only 1. Mod Z only 1. Okay. So therefore, if you substitute this mod Z 1 here, 1 minus 1, 1 minus 1 squared divided by 1 minus z. People remember, mod z equals 1 does not imply z equals 1, no? Does not always imply z equals 1. Z equals 1 is only one solution. There can be complex numbers. Complex number is not equal to 1, but modulus is 1. Right, people? Now you can very clearly see here. I can very easily prove that. Consider on the Argand plane a circle with radius 1 and center at the origin. Then any complex number on the circle, when we consider people, its modulus is 1. Then how many complex numbers we can have so that the modulus of the complex number is 1? Infinity. Among them, people, when I consider the complex number, this, since the radius is 1, this complex number is 1. Among them, z equals 1. 1 is only one case. So therefore, in the question you are given z not equal to 1. Therefore, this z not equal to 1, then 1 minus z never be equal to 0. Therefore, its mod never be equal to 0. Then this has meaningful. Mod z1, since mod z1, this is 1, 1 squared is 1, 1 minus 1 is never 0, then this is 0. That says what? Real part of W0. Then we were this part 0. Then what is W? Equals I, this. Understand? Right. Then we can write W complex number. We can write W complex number. Therefore, this W complex number you can write as I times 2 imaginary part of z divided by 1 minus z mod perfect square. Right. Now, people, we have substitute for this. What is the imaginary part of z? Z this no? Imaginary part of z is people sin alpha. Then we can write W equals I 2y now. 2y, I am z means sin alpha. Divided by modulus 1 minus z cos alpha plus I sin alpha. This way we have. Right. Now we have to simplify this little bit. This is perfect square, no? I minus z perfect square. Then we can write W equals 2I sin alpha divided by, I can write this one as how, people? 1 minus cos alpha minus I sin alpha. Right. Within modulus sin perfect squared. People, what is this within modulus sin? This, if I consider as x, this minus sin and this sin alpha, if I consider as y, what do you have here, people? X plus IY. We have a complex number within the modulus. Then what is asking? The perfect square of the modulus of the complex number available here. How to write the perfect square of the modulus of a complex number? Real part squared plus imaginary part square. That is the perfect square of the modulus of a complex number. Understand? Right? Yeah. Then I can write the modulus perfect squared of this way, people. I can write it like this. 2i sin alpha divided by 1 minus cos alpha perfect squared plus minus sin alpha perfect squared. Now simplify this. Then you get this answer. You get this answer. Let's simplify this. What do you get? 1 minus 2 cos alpha, cos squared alpha plus sin squared alpha. This is 1. Right now, I expanded this using a minus b perfect square form. Then what do you get? W2i sin alpha divided by 1 and 1 make 2 minus 2 cos alpha. People, you can cancel down this 2. With this 2, here we get 1. W equals I. This sin alpha, people, you can write as 2 sin alpha by 2 into cos alpha by 2 divided by 1 minus cos alpha. This cos alpha we can write as, people, 1 minus 2 sin squared alpha by 2. Cos alpha we can write as 1 minus 2 sin squared alpha by 2. Then here, remove the bracket. 1 minus 1 we can cancel down. Minus minus make plus, right? We get W I times 2 sin alpha by 2 into cos alpha by 2 to sin squared alpha by 2. This and 1 sin alpha by 2 can cancel down. This and this we can cancel down. Cos by sin is cot I cot alpha by 2. This is the W complex number. Right. Okay, people, the next part of that. Read the next part. Right. Read the next part, people. The next part is really given this way. In an Argand diagram, the points A and B represent the complex numbers minus 3i and 4 respectively. The points C and D lie in the first quadrant. All right. We'll see what is that. Let's say we have Argand plane, Argand diagram. Real axis. Imaginary axis. Here we have point A. The point A and B represent complex numbers minus 3i and 4. Point A represent complex number minus 3i. Minus 3i means people, complex number is 0 minus 3i, no? Real part 0, imaginary part minus 3. The point that represent is 0 minus 3. This is the complex number minus 3i. A. B represents the complex number 4. Complex number 4 means people 4 plus 0i. Then that corresponding point is 0, 4, 0 here. This is B. Complex number 4. Right. Now, the points C and D lie in the first quadrant such that ABCD is a rhombus. ABCD is a rhombus. ABCD. ABCD is a rhombus. And even BAD theta, this is theta. And given that sine theta, 7 upon 25, no? Find the complex numbers represented by the point C and D. This and this. Yes, people, how to take that now? This is a rhombus, no? Then this length, this length, this length, this length being equal. Okay. Then can somebody tell me how to find the complex number at the point D? Can someone tell me by using what theory directly we can find the complex number at D? Yeah, people? That rotation theory? The rotation theory? Can you remember that theory? This length and this length being equal, theta measured in counterclockwise. This is Z1, Z0, this is Z2. The way of writing the complex number given by this line Z2 minus Z0 is equal to the complex number given by this line is Z1 minus Z0, but cos theta plus I sin theta. That you can very easily use here because this length and this length being equal. Then the complex number given by this AD line is complex number at D minus complex number at A. What is that? Is it D minus here this complex minus 3i equals this complex 4 minus 3i. Times what? Cos theta plus I sin theta. Cos theta plus I sin theta. Right? Cos theta plus I sin theta. But for this triangle sin theta, we can find cos theta. Here theta 7, this is 25, right? Sin theta, no? right? Okay, then here we get 24 this. 25 squared is 6. 25 minus 49, no? It's root 24. Then cos theta we can write 24 by 25. Then Z D you can subject. Take this plus 3i to right hand side minus 3i plus this is 4 plus 3i. Substitute for cos theta 24 by 25 plus I times 7 divided by 25. Then Z D, people simplify this. We get this is a D when you simplify this. Simplify that, people. 3 plus I. Hmm? 3 plus I. Now tell me how to find the complex sum at C, ZC. This is a rhombus now, people. When this is a rhombus, you know the diagonal bisect each other like this. These two are equal, these two are separately equal. Therefore, the complex number representing by this point can be written in two ways. This complex number plus this complex number divided by 2. The same thing you can write this plus this divided by 2. Then you can find what? The ZC, right? Then you can write ZC plus this complex sum minus 3i divided by 2 is equal to 4 plus ZD 3 plus I divided by 2. This and this you can cancel down. ZC you can find. How? It is coming 7 plus 4i after simplifying. So 7 plus 4i. Okay, people. Right. Now, another few questions, people, we have to do. But anyway, next Friday, I come to the Adimov's theorem part. Then by that, we can come to the end of this complex number part. Right? Okay.